And what we're going to do, I've just started the recording. What we're going to do today is try to catch up a little bit behind. Unfortunately, for a course like this, there's a lot of material that needs to be covered because it is a core course and we have to cover pretty much everything that's in the curriculum. Otherwise, you're not prepared for the final. Um, so whenever I fall a little bit behind, which inevitably happens, I have to catch up. And today's one of those days. Um, Now, as far as homework is concerned, I did put out a homework assignment, which was due at 12:30 today, and I was seeing there's quite a few people still had not completed it. So I probably will extend it till the end of today. Okay, it's fine. So Sunny, that's okay. Um, all right. I don't know if he heard me. Okay. So anyway, as far as the homework is concerned, I've reduced the percentage from 15% to 10% and increased the percentage for group quizzes to 20%. And I think that might be a little better for you. So that's changed. I'll probably update the syllabus sometime in the near future, just reflect that. There will be a second homework assignment because I do want you to practice some of the things I'm going to be covering today. I want you to have some practice with that. And But as far as the homework is concerned, I'm giving you 3 attempts. Now, the attempt is a little different than homework systems that you might be used to. I don't really have a homework system built inside of Canvas, sort of create my own. So when I say there's 3 attempts, I'm talking about the entire quiz has to be attempted again. Um, and So you may want, as you go along, you may want to um, write down your responses, even though they are reported afterwards. You may want to, keep the notes that you're taking as you go along when you're doing the homework questions. You may want to keep them, and if you're going to do a second and third attempt, which I'm assuming many of you will do. Um, as far as doing the homework, I know that you have other classes and you probably, unless this is something that you're interested in, you want to probably put this, if you're taking 4 classes, this is your 4th class in terms of time committed to it. But I can tell you that the more time you can put into this class, the better your ultimate grade will be. And if what I'm covering in class is not clear, you do have the recorded videos. You should go back and listen to them again, and probably do that before you actually do the homework. Now that does take time because each class is over an hour. But again, it might be worth your effort to do that. If you don't do that, then I think if you just take the quiz sort of in a unprepared way, it's going to be more difficult. Also, reading the examples in the textbook can help. What I'm trying to do in the homework is give you sort of the types of questions I might ask on your test. It may not totally reflect what's on the test, but it will reflect at least some of the things that I'm interested in having you learn. So some of the homework problems which come from the book, I'm not asking you necessarily to answer the questions as they are posed in the book, but I might ask you different questions. And I'm more interested in the questions I'm asking as opposed to what the book's asking. As far as the histogram is concerned, the book doesn't really go through the way I'm teaching it, and the way I teach it is actually the way the calculator does it. So that's why I teach it the way that I do, because it matches what the TI-8384 calculator does. So please follow the way I do it, the way the calculator does it. And I think as far as the histogram is concerned, you'll definitely need to see that video once again. Watch that one again. All right. So this is just some advice for you in terms of doing the homework, because I was looking at the grades and some of them were not very high, and it's maybe And I looked in, and I'm also given reports about how much time you're spending on the homework. And, if you're only spending 20, 30 minutes on the homework, it's probably not enough. That's my take on it, unless, of course, it's something that seems easy to you and you don't have to spend much time on it. But I would think that's not the case for most of you. So you'll need to spend more time on it. And again, I can't tell you what to do because you have other time commitments, but 20, 30 minutes on homework a week is probably not enough for many of you. So the wording in the homework was a little confusing. You talk about from the book itself. Emilio, could you, is it the wording from the book itself that's confusing to you? Can you just, or you can just say out loud if you want to unmute yourself. Let me know what you're referring to when you say it's confusing. Hello, Emilio?
Yeah. There were some like problems in the homework they were just like I couldn't understand what you were asking specifically.
Okay, could you give me an example of that?
Yeah, I think I could go back. I'm not sure if I could.
Yeah, write down, whenever you have an issue with something, please write it down so that you can let me know and I can correct anything that might be confusing to you. But you don't
Uh,
have to do it right this second. If you don't have it right,
yeah, no, I don't have it, but yeah, I'll let you know.
yeah, let me know. Anybody else with that issue? Maybe you're not clear about what's being asked. All right. I think I think it's time for most of you, mostly time. So just put a little more time into it, and then you'll see better results, I think, from doing this course. All right, but any issues with clarity, you should always let me know. Send me emails even. If you're doing the homework and you're not sure about what something means, send me an email and I'll respond to it. Okay, don't be shy about doing that. All right, so okay, all right. So we're gonna continue with chapter 4, and let's share the screen. Now, if many of you are not paying attention, I mean, I see many of your videos are off. I had to ask you to put the video on if you don't want me to see what you look like, or if you're not paying attention. That's probably not a great idea. If you're just here because you want to show that you've attended, but you're not paying attention, you might as well pay attention because this is your class and you want to get a good grade, and you need to do that. So again, if you're not paying attention, if you're on your cell phone doing other things, it's probably not in your best interest to do that. But again, I'm not here to. I'm not your parent. I'm not going to shame you or anything like that. But I do want you to understand that the more effort you put into this course, the better your grade will be, and that's what it all boils down to. All right. So chapter 4, section 4. I think section 4. I think that's where we're in, and these are rules that I teach in every statistics course, and that has to do with the um, issues of center and variability of the data. Remember, the center is something that represents the entire data set. It's sort of a number that's in the middle. Variability has to do with how spread out the data points are. And the whole idea of variability, I should make this really clear to you. Variability is important in statistics because the more variable your data is, the less representative the center of the distribution is. It's hard to say, if the data points are really spread different, very, very different from each other, then the mean is not going to really represent the data points very well. So that's why we have to know about variability. The mean is not just enough. It's not enough. How variable the data is also important. So that's why we're talking about it here. Typically, in this section here, when we talk about interpreting the center and variability, we're going to use the mean and standard deviation. We're not going to use the median. We're not going to use the interquartile range. We'll use the mean and standard deviation in this particular section. All right. clear to you. Now, suppose we're looking at a population of test scores. This is pretty common. So you have a standardized test, and suppose for a standardized test, the mean is 100, and the standard deviation is 15. Now, the standard deviation is sort of the average spread of the data. That's the way to look at it. All right, it's the average spread or variability of the data, and it's in the same units as the mean. So if the mean is um, maybe instead of test scores, we'll talk about height. If height is in inches, then the mean and standard deviation would both be in inches. All right, so the units of measurement are the same. So the mean is the center of the distribution, standard deviation is the spread of the distribution. So if we say the mean of a bunch of test scores is 100 and the standard deviation is 15, then one thing that we could do is we could take the difference between the mean and the standard deviation. All right, take the difference between those two numbers. And suppose we did that and we got a test score of 85. So we subtracted 15, the standard deviation, from 100, and we got 85. One thing we could say about 85 is that it's one standard deviation below the mean. And what's one standard deviation? It's 15 units here. 15 represents the standard deviation. So if 85 is 15 less than 100 and 15 is the standard deviation, we can say that 85 is one standard deviation below the mean. In a similar way, if we add 15 to 100 and we get 115, we could say this test score 115 is one standard deviation above the mean. All right, hopefully that makes sense to all of you. That we're simply adding up the standard deviation, adding it to the mean and saying 115 is one standard deviation, which is 15, bigger than the mean, which is 100. All right, so when we talk in this way, this is what we mean. All right, and this is something that we will be talking. We're going to be using this type of English in this course. If this is confusing to you, you'll have to get used to it. There's no other way of saying it. You just have to sort of learn it. It's like any other language. This is a different language. Like you're learning French. Well, French is different than English, so you have to learn how to use it. And in the same way, statistics is different than anything else that you've learned and has a certain language to it. So you have to learn the language. So if it is a little confusing at first, join the club. Everybody feels that way at first, but you have to put a little effort into it and learn the language. And that's really what I'm trying to teach you also, is the vocabulary, the way of saying it. It's different, that's all. It's the only thing I can say. Now, let's get to the next slide here. Suppose we took two standard deviations. When we say the terms two standard deviations, you simply multiply 2 times whatever the standard deviation amount is. So if standard deviation is 15, and we say 2 standard deviations, we simply multiply 15 times 2, and we get 30. So if I want to find a test score that is 2 standard deviations lower than the mean, and the mean is 100, I simply multiply the standard deviation of 15 times 2, which is 30, and I subtract it from 100. When I do that, I get 70, right? Because 2 times 15 is 30. 100 minus 30 is 70. So the score 70 is 2 standard deviations less than the mean. In the same way, 130 is 2 standard deviations above the mean because we add 30 to 100 and we get 130. All right? Everybody clear about that? Okay. And how about 3 standard deviations from the mean? Well, 3 standard deviations is 3 times 15 is 45. That's 3 standard deviations. So if we subtract that from 100, we're going to get what? Well, 100 minus 45 is 55. So it's 55. The score 55 is 3 standard deviations less than the mean. And 45 plus 100 is 145. That's 3 standard deviations larger than the mean. So statisticians, people who do statistics, that's the language they use, all right? And that's what you sort of have to understand and get used to when you take this course, because we're going to use this language for the rest of the course, All right, so now you're going to be learning this language, and that's why this particular section is important. All right, it's not, we're not trying to, torture you in any way. We're just trying to have you learn this language. All right. So, um, so what they're saying here is sometimes in articles they quote the mean and standard deviation, but they don't give you any graphical display. They don't show you a box plot. They don't show you a histogram, nothing like that. So you have to sort of do your own little calculations, all right, to determine what the meaning of the mean and standard deviation is for that data. So one rule that came up, and this is a rule that's been around for about 100 years or so, over 100 years, is called Chebyshev's rule. Chebyshev was a Russian mathematician. And he found something really, really interesting. It doesn't really state it here, but I think it might state it more in the book. What he found was, he says, no matter what your data is, and what he meant by that was, he says, it could be symmetric, bell-shaped, it could be skewed left, skewed to the right, it doesn't matter. He says he found mathematically that there was a certain percentage of the data that was between a certain amount of standard deviations from the mean, all right? A minimum amount of data. And it was pretty remarkable he found such a formula, but he proved it. And the formula looks kind of, well, it's not really that complicated, but it looks a little complicated at first when you look at it. So what it says is that pick a number and they call it K, all right? K is some number that's at least 1. And it doesn't have to be an integer or a whole number. No, it could be a decimal. And it says the following. It says the percentage of observations that are within K standard deviations of the mean is at least, and then you calculate this percentage. Now, when they say within K standard deviations, now let's go back to what I just said a minute ago. When I said a test score was 2 standard deviations less than the mean, and then I said a test score was 2 standard deviations greater than the mean. When they use the word within 2 standard deviations, what they mean is between 2 standard deviations less than the mean and 2 standard deviations greater than the mean. In other words, between those 2 values, that's what they're talking about, the percentage of data between those 2 numbers. So let's just go back and let me just make that real clear here. For example, if you look over here, if I wanted to know the percentage of data between 2 standard deviations from the mean, what I'm saying is between 70 and 130. That's what I'm asking for. The percentage of data that's between 70 and 130. That's within 2 standard deviations of the mean. So you subtract it from the mean, you add it to the mean, all right? And then between those 2 values, 70 and 130, we're asking the question, what percentage of the data is within 2 standard deviations of the mean? All right, that's what they're talking about with Chebyshev. All right. All right. Now, how do you do it? Well, you simply plug in the number K, whatever K is. If I tell you I want to know the minimum percentage data between that is within 2 standard deviations of the mean, you plug in the number 2, which is K, into this formula. Well, the denominator of this fraction is K squared, so you plug in 2. We know that 2 squared is 4. So what's inside the parentheses is 1 minus 1 over 4, and that's 3 over 4, which is 3/4, all right? So when you convert it to a percentage, that's 75%. So what this formula is telling you is that a minimum of 75% of data for any data set is within 2 standard deviations of the mean. 75% of the data is always, at least 75% of the data is always within 2 standard deviations of the mean, no matter what the data set. All right, that's what it says. Now, if I put 1 into K, well, 1 squared is 1, and then 1 divided by 1 is 1, 1 minus 1 is 0. Then it says at least 0% of the data is within 1 standard deviation of the mean. Now, that's kind of useless information. That doesn't say anything. So really, we have to start with some number bigger than 1. Otherwise, we're going to end up with some nonsense with this formula. So if we plug in 2 here, we get 75% of the data is within 2 standard deviations of the mean. If k is equal to 3, and 3 squared is 9, 1 minus 1/9 is 8/9, and I believe that comes out to something like 88.9%. We can say at least 88.9% of the data is within 3 standard deviations of the mean, like that. You all have calculators, you could figure it out. And you could also put this on a piece of paper too. I think there's even a chart in the book that lists all of those. You plug in 2, you plug in 3, plug in 4, all the way up to 10. There's no, we never talk about 10 standard deviations from the mean, all right? It's usually 2 or 3 or something like that. All right, so that's Chebyshev's rule, and it's a neat little thing, and something you should know for this course. And they give you, here's the chart. Here's the chart that they're talking about. So if you plug in 2 for k, you get 75%. You plug in 3 for k into the formula, you get 89%. They're rounding it to the nearest whole number for percentage. You plug in 4, you get 94%. All right. I don't know why they put 4.472 in here, because it comes out to 95% for some reason.
Professor.
Yeah, go ahead. You have a question.
You said no matter what the numbers are in the data set, it's always at least 75%.
Yes. It's pretty remarkable, isn't it? You think you just make up a data set, and it doesn't even matter. It's within 2 standard deviations of the mean, at least 75% of the data will always be there. Within 3 standard deviations of the mean, 89% of the data will always be there. That's what it's saying. It's pretty remarkable, the result. So that's Chebyshev, and it deals with any data set, all right? So typically, if I tell you in a test question that the data set is skewed left or skewed right, it's skewed. It's not symmetric, all right? Then you can use Chebyshev to answer a question about data in between, within a certain number of standard deviations from the mean, all right? And that's it. That's all there is to Chebyshev. And they give more examples here. You could look through them. And the whole idea of giving more examples is so that you could see other examples where the mean is a certain number. In this case, the mean, what is the mean? 36, standard deviations 12, all right? So within 2 standard deviations of the mean, if the standard deviation is equal to 12, then 2 times 12 is 24. So that's 2 standard deviations. You've subtracted from the mean of 36, you get 12 on the left. And if you add 24 to 36, you get 60 on the right. All right. So again, they're trying to give you more examples. Take a look at the slides, take a look at the book. It's all the same thing. And the only thing you have to know are those percentages. And again, you don't have to memorize them because it's open book. So you guys are very happy, right, about this, because you take this course in person. There's no open book. It's closed book. You have to memorize all. Not memorize. You have to use formula sheets. Usually in class, I would tell people to create formula sheets. So they would put Chebyshev in the formula sheet. But here, I'm just saying use your book. All right. So go ahead and do that. All right. And then you should just look at these examples. Now, the other rule that you have to know about in this chapter in terms of distribution is called the empirical rule. And I'm telling you the empirical rule is only for the bell-shaped curve, the normal curve, all right? The curve that looks like this, all right? So only for this is the empirical rule. So you can use the empirical rule for bell-shaped curves, but you cannot use it for curves that are skewed left, skewed right, or anything that doesn't look bell-shaped. You can't use it. You should use Chebyshev instead. The same type of questions would be asked. What's the percentage of data between 1 standard deviation from the mean, 2 standard deviations from the mean, and so forth? For bell-shaped curves, it's very, very clear. The answer is within 1 standard deviation of the mean, the percentage of the observations is about 68%. So they give you not a minimum, they give you the percentage. For within two standard deviations of the mean, it's 95%. And within 3 standard deviations of the mean, it's pretty much the whole curve. It's 99.7%. So, most data isn't perfectly normal, but if it looks reasonably normal, you can use these percentages here. Okay. So this is what we use for bell-shaped curves. We use this particular rule. Now we can get kind of fancy with this, all right? Because with Chebyshev, we can only answer the question, what percentage within 1 standard deviation, what percentage within 2 standard deviations, 3 standard deviations. That's all we can ask. With this here, we can actually be a little fancier, all right? And what I'm saying is we can ask the following question. We can ask, what if we find what the mean is, all right? If we know what the mean is and we know what the standard deviation is, we can calculate all these data points down here, right? Because if the mean is 100 and the standard deviation is 15, like the previous example, that means 1 standard deviation bigger than the mean is 115, 2 standard deviations of the mean is 130, 3 standard deviations 145. You just keep adding 15, which is the standard deviation. The same thing below the mean. You would subtract 15 to get 85. We subtract another 15 to get 70. We subtract another 15 to get 55. All right. So we can get fancier here for the following reason. With a bell-shaped curve, it's symmetric. It's symmetric. So we can draw a line right down the middle. We know the mean is equal to the median with a bell-shaped curve. The mean is equal to the median. So if the mean is equal to the median, that means 50% of the data is less than the mean, and 50% of the data is greater than the mean. We can't say that with a skewed left or skewed right curve because the mean and median aren't equal to each other. So we can't say that. We can only say that here with the bell-shaped curve. So if that's true, then we could also talk about symmetry within each of these halves of each side of the curve. So for example, now what they did here, interestingly, was they took the 68% and split it into 2 34% pieces. And that's because of the symmetry. The area under this curve here between 1 standard deviation less than the mean and 1 standard deviation greater than the mean, this symmetry, these 2 pieces are equal in area. They're equal to each other. It's because of the symmetry. Again, we can't say that with a skewed curve. It doesn't work that way. So we could split this into 34%. Now notice this. So they create these pieces here. So look at this tan piece here, brown tan piece here. They say 13.5% is in between these two. The question is, where do they get the 13.5%? Where did that come from, right? Well, we know where the 34% came from because that's half of 68. Now we know from 2 standard deviations from the mean, it's 95%, right? Between this number here and this number here is the area under this curve here is 95%. So 68% is in these 2 pieces. 95 minus 68 must be in these 2 pieces. 95 minus 68 is 27. And then because these 2 pieces are because of symmetry, are equal to each other, you just take half of that 27 and you get 13.5. In a similar way, these green pieces represent areas that are beyond 2 standard deviations up to 3 standard deviations. So this is 2 standard deviations. You can't see it, but there's a little notch over there, little notch over there, representing 3 standard deviations from the mean. Remember, that's 99.7%, 99.7%. And when we calculate what should be the total of these 2 green areas, it ends up being 4.7%. And we take half of it, we get 2.35%. If we add all of these numbers up, we should get 99.7%. And that represents the 3 standard deviations from the mean, 99.7%. So if you have this curve in front of you, if you print this out, which I would recommend, just print it out. And whenever you take a quiz or test, have this in front of you, or even when you do your homework, have this in front of you so it'll be clear. If I said, for example, let's say the mean is 100 and the standard deviation is 15. Now I wanted to know what percentage of the data is greater than 85. Well, 85 is over here. 85 is one standard deviation less than the mean, right? 100 minus 15 is 85, right here. Now I want to know what percentage of the data is greater than 85. Well, what do I do? I just add up these percentages. 34 plus 34 plus 13.5 plus 2.35, and there's my answer. If I wanted to know, for example, what percentage of the data is between 85 and 130. So 85 is here, right? One standard deviation is less. 130 is two standard deviations more. Once again, I just add up the areas, the percentages up to between those 2 points. So it'll be 34 plus 34 plus 13.5. That's it. Just have this in front of you, and you can answer any of those questions. The thing that you have to do is you have to, for that particular problem, write in the mean, right below the word mean here, write it in, and then figure out what all these data points are here. If the standard deviation is, for example, if the mean is 80 and the standard deviation is 10, then you write 80 below the mean, and then 10, one standard deviation is 10, so 80 plus 10 is 90, so you put 90 here. And then you add another 10, you get 100. Add another 10, you get 110, like that. And you subtract 10 as you go down that way. So just label your normal curve, and then you can figure out any of those types of questions. Any questions about that? Because this curve here, very beautifully printed, written, and you can easily figure out how to do these types of problems. Otherwise, if you don't have the visual in front of you, it can be a little difficult, because then you have to mentally take a picture of it in your mind, and it's a little more difficult. All right, and then they have several examples of that. All right, and then the other thing that they have in this section here is what's called a z-score. We're going to use this throughout the course. Very, very, very important to know how to do a z-score, and it's not hard to do. So suppose once again we have the test that we had before with a mean of 100 and standard deviation of 15. Suppose we wanted to find the z-score for a test score of 115. So you got a score of 115, and you want to convert it into, now first of all, your score of 115 is called a raw score. You might, again, if you took the SATs, you've probably seen these words before. Your raw score was your actual score. So let's say you took the math SATs and you got a 550 out of 800. I don't know if they score it that way anymore, but let's assume that's what they do. And that's your raw score. And then they have a standard score. They give you the standard score also. So a z-score is a standard score. And the way to calculate a standard score, or z-score, is you take your raw score, your value, subtract the mean in the numerator, and then once you've come up with that difference, you divide it by the standard deviation. And what the z-score tells you is how many standard deviations your score is from the mean. Now, if it's a positive z-score, it means that you scored better than the mean. And if it's a negative z-score, you scored less than the mean. So if you had a z-score of, let's say, 1.3, that means you scored 1.3 standard deviations greater than the mean. That's what it means. If you had a z-score of negative 0.2, that means you scored 2 standard deviations less than the mean. That's what it means. The number of standard deviations, either bigger or greater, and the sign of the z-score tells you whether it's bigger or smaller, and the number itself tells you how much how many standard deviations. Okay, and that's a z-score, and it's very important for this course. We're going to be using it over and over again. All right. And they give you an example here, and the reason why do we use z-scores is because if we're doing comparisons between different groups, then it makes the comparison better. It makes a better comparison. Let me give you the example here. Suppose two people are applying for jobs. All right, one person's an accounting major, the other person's a marketing major. All right, and suppose the accounting major has an offer of $55,000 per year, and the marketing student has an offer for $53,000 per year. Now, you could say, all right, the accounting major is making more money. But in a sense, are they really doing better than the marketing student is? If you compare these two students, which one is really doing better? Well, if we look at it relative to the average person, what the accounting person does, and what the marketing person does, and also the variability of those two groups, we may come up with a different conclusion. For example, for accountants, the average for accounting majors is $56,000, right? With a standard deviation of 1,500. For marketing, it's lower, 52,500 with standard deviation of 1,000. So the first thing we know immediately is that the accounting person is getting an offer that's less than the mean. That's number one. And the marketing person is getting an offer that's greater than the mean for their group. All right. But what we should do, however, is calculate their z-scores, because that tells us how many standard deviations above or below. So the accounting person is getting being offered a salary below the mean of 56,000, and the marketing person is getting one above. But we need to calculate the z-score, and we do that. We see that the accounting person's offer is negative 0.67 standard deviations from the mean, or we could just say 0.67 below standard deviations below the mean. That's another way of saying that. $55,000 offer, and the marketing person is getting an offer which is 0.5 standard deviations greater than the mean. That's positive. So who's doing better in this case here? I would say the marketing person's doing better. If you compare the two groups, relative to the two groups, the marketing person got the better job. All right. We're not looking at it from an absolute point of view. We're looking from a relative point of view, and we always have to compare the two groups. And in this case, relative to the marketing group, the marketing person's doing pretty well. Relative to the accounting group, the accounting person's not doing as well as far as salary. All right, and that's why we want to calculate z-scores. All right, now they mention here, and this is something you'll sort of get a feel for, that a z-score outside of the interval from -2 to +2 occurs for about 5% of all observations if we use the empirical rule. For the empirical rule, if we calculate the percentage of observations that are outside of the range of -2 to 2 standard z-scores, then that's about 5%. That means between -2 and 2 is about 95% of all observations, approximately. And even if we go out a little bit and say between -3 and 3, we say any z-scores outside of that range is very, very rare. It's only 0.3% of the time. But you'll get a feeling for this later when we use these z-scores. The final concept is percentiles. This is something, if you, again, took the SATs, they would give you a percentile. Percentile means, for example, if I say the 50th percentile, what I'm referring to is that that 50% of the data is less than or equal to that number. So, if we have the empirical rule and we know that the mean is 100, we also know that's equal to the median of 100. We know that 50% of the data is going to be less than 100, 50% is going to be greater than 100. So percentile, that's what it means. So 50th percentile, 50% below, less than or equal to. If I say 90th percentile, that means 90% of the people, let's say it's a test, 90% of the people scored less than or equal to that score. I said 20th percentile, that means 20% did worse, but 80% did better. And I think hopefully all of you are familiar with the term percentile. All right. So that's an important concept. Do we have many questions on tests about percentiles? A little bit, but not a great deal. All right. They do, if you had a chart like this, and if they told you what the percentile values were, you would notice that they would go up as the percentiles went up. So what are they saying here with head circumference? They're saying 5% of the population has a head circumference less than or equal 32.2. 10% of the population has head circumference less than or equal 33.2 centimeters. 90% of the population has percentile has head circumference less than or equal to 38.2 centimeters, like that. Okay, so that's how you read that chart. Any questions about that? I think you've seen this before. This is not something new with this course, percentiles. And then here's a little subtle little point they're trying to make here. Suppose we graph this sort of thing, and we notice that the 95th percentile is 38.6, the median is 35.8, and the 5th percentile is 32.2. Then this would be a skewed left distribution, right? And why would that be the case? Is because the distance from the median to the 5th percentile is bigger than the distance from the median to the 95th percentile. Remember, the 5th percentile says 5% is less. The 95th percentile is actually saying 5% is more. All right. So if these two areas are the same, but the distance is different, then you know that it's going to be skewed. In this case, skewed to the left because there's more. There's 5% of the data that's less than 32.2, and there's 5% of the data that's less than 38.6. And I think this hopefully makes some sense to you. All right, and if it was the opposite, if the if the distance from the median to the 95th percentile, that distance between these two numbers here is greater than the distance from the median to the 5th percentile, then it would have been skewed to the right. Okay, any questions about that? All right, so that is the end of chapter 4. Now, what we're going to spend the rest of the time on is and it looks like a lot of material, but it really isn't, is we're going to go back to chapter 3 for a moment. So let me unshare. And I'm going to go to section 3.4. All right, this is section 3.4. And let me just explain to you, for most of this course, we're just going to be looking at statistics with reference to one variable. In real life, we never do that. We're always looking at multiple variables, and researchers and people who do data analysis. It's never one variable. But again, this is a statistics course. We're trying to keep this as simple as we possibly can. But as part of this course, we will look at one situation where we will be comparing two variables. And it's basically a situation where there might be a cause and effect relationship. In other words, one variable seemingly is causing the other variable. Now, we talked a little bit about experimental methods, right? And we were talking about an explanatory variable causing a response variable, right? And you would try to control for confounding variables and things like that. But here we're actually going to do some analysis. And fortunately, you have the TI-83 or TI-84 calculator because it does all the work for you. Because when I went to school many years ago and I took statistics, the formulas that you will see in chapter 5 is, we had to do it all by hand. We didn't even have calculators. Everything was done by hand. So it was very tedious, cumbersome. But you have your calculators. It becomes very easy. You just have to know the steps. All right. And this course is all about knowing the steps of how to do things with a calculator. It really is. And if you learn that, this course is not that hard. So we're going to look at what's called bivariate data. That means two variables. And it's numerical data. And we're going to look at a possible cause and effect relationship. We're going to skip the time series part here. So please do not spend your time on the time series, all right? Because this just makes things a little more complicated, and I don't want to deal with those complications. But one thing that we will be looking at, and actually it doesn't seem like, I thought the slides would go into scatter plots. All right. So the PowerPoint slides here do not go into scatter plots, and unfortunately, I'm actually going to remove this section from the because in a previous version of this textbook, this section had to do with mostly with the scatter plots, but they don't have it here. But don't worry about that because I will show you how to do the scatter plot. So this section I'm actually going to remove from the course. I won't even bother with it. It's kind of useless. It's not going to help you. So I'm going to go right into chapter 5. So don't worry about 3.4. This PowerPoint slides. Now in the textbook, they do go through the scatter plots, but don't worry about it. It's covered in chapter 5 also. So go to chapter 5. All right. All right, chapter 5, and let's see if I see it here. Correlation, that's the one I want. All right. And let me just take a quick look at 3.4 in the textbook. And it's a little annoying that they remove that material and scatter plots in there. All right. Give me a second here. All right. In your textbook in section 3.4, if you're going to read about scatter plots, it's just 3 or 4 pages. It's from page 116 through 119. But they don't have it. They don't have any PowerPoint slides for that. So you can read through it, but I will discuss it anyway. So don't worry. Correlation. What does correlation mean? Well, if we're going to look at a relationship between two variables, what we're going to look at is basically the trend of the two variables. In other words, if they're both numeric variables, we might want to consider what happens to one variable when the other variable is increasing or decreasing. Do they both go up at the same time? Do they both go down at the same time? Or is there no relationship at all? That's really what we're going to look at. And some of you who have been in high school recently, within the last 2, 3, 4 years, know that this is a topic that's now covered in Algebra 2, all right, where you're using your TI-8384 calculator to look at correlation, look at the relationship between two variables. And that's all we're going to do in this course. This course, we're not going to go beyond a high school understanding of this, all right? It's strictly high school. So again, those of you who've been through this before, this is going to be an easy topic. If you've been out of high school for a while and did not learn this in your high school Algebra 2 course or didn't take Algebra 2, no worries, because I'll show you exactly how to do it. It's very easy. All right. Now, I should let you know that this particular chart here is important. This one here. This is again section 5.1. It's the 4th slide. And the reason it's important is because this is covered in the final exam. All right, and also obviously in the exam I'll be giving to you also. And suppose we have two variables. We have an x variable, and this is the same thing we used to do in algebra. We have an x-axis, a y-axis, and then we have these dots represent xy points. All right, so if we have, let's say we're comparing height and weight for 50 people. Well, each person would have, let's say the height is the explanatory variable, and the weight is the response variable. We're saying that let's say our theory is the taller the person is, the more they should weigh. All right. So along the x-axis is going to be what? It's going to be our explanatory variable. All right, along the x-axis, explanatory variable, that's the height. Along the y-axis is our response variable, that's our weight. All right, and these dots represent x, y points for each person. All 50 people, we asked their height and weight for 50 people. We would get 50 x, y points, and we would plot them just like we used to plot them in high school. All right, no different. All of you taken this before, you all know it. Now, what we notice in this plot here, the first one, is that we have a positive linear relationship. That means as x increases, y increases. We see the trend going up. This is similar to the idea of slope. All right, if we drew a straight line through these points, the straight line would be sloping up to the right, which means as x increases, y increases. All right. This one is a very strong relationship because if we drew a straight line through these points would be very close to the line, would be sort of hugging the line. B is also a positive linear relationship. All right, we can picture drawing a straight line through it, but there's a little more scatter around that line. All right, the points aren't as close to the line as the first one would be. C would be a negative linear relationship. It actually is even more scattered than these other two, but it's negative. That means as x is increasing, y is decreasing. Negative linear relationship. This one is sort of like a cloud. It doesn't seem to have any relationship. And this one has a strong relationship, but it's not linear. It's curved. You see the curve? You draw a curve through it. So this is a curved relationship. Now, correlation is a measure of linear relationship, which means the following. This last one here, this curve relationship would not be applicable. It's not linear, it's curved. Even though it's a strong relationship, if we calculated the correlation, it would be close to zero. It would show no relationship, no linear relationship, and yet it is a strong relationship, but it's curved, it's nonlinear. So correlation would not apply in this case here. We would not use it for case E. For case D, yes, we could do a linear relationship between this because it's not curved, there's no trend at all, but it would be sort of a horizontal line that would go flat through this, and it would be a zero relationship between the two. No, so it would apply, correlation would apply, but we would say zero for the linear relationship. This one would have a negative linear relationship, and these two would be positive. All right. So correlation measures two things. You should write this down. This is very important. Correlation measures the strength and direction of a linear relationship between two numeric variables. It measures the strength and direction of the linear relationship between two numeric variables. The direction is whether it's trending up or trending down. So going up, going down, or not going anywhere, which is zero. Right? But it's measuring a linear relationship. That's why this E one, this curved one, doesn't apply. It's not applicable for correlation. Okay. So this E, if we were asked on an exam, does correlation apply in case E? You'd say no. These other four cases, you'd say yes. All right, they apply in all four of these first four cases. All right, so let's go to the next slide. Okay, so that's direction. How about strength? Strength means that the points are hugging. If we drew what we call a best fitting line, a line with best fit these points, a straight line, these points would hug the line pretty closely. That means strong. If they're more scattered like this one over here, it means not as strong. Right? That's what we mean by strength. how close are those points to a line, a line that's you could draw through those points. Okay. Obviously, this one has no relationship. It would be 0, would be the strength of D. All right. So strength and direction. All right. All right. And then he talked about, of course, negatively related, positively related, no relationship. And that chart that I just showed you a minute ago, those 5 cases, you can see it. Now, the correlation coefficient is a little complicated to calculate. You can do it, but it requires some agility with mathematics, okay? And I know some of you, math is not your strong suit, right? You're taking this because you have to. But you know that math has been a little bit of a struggle for you. No problem, because you don't have to use this, this formula here. You can do what's called using your calculator. All right, you're going to use your calculator to find it. So how do we find this thing called the correlation coefficient? Let's go to the calculator. And you should have your calculator with you. If you don't, you're going to have to watch this again. As I mentioned, your calculator should be with you for all the meetings. Right? Let's get to the calculator, and if the calculator is relatively new, you haven't used it before for statistics, then you probably need to do the following step. Now, what you're going to need to do is, and follow along, is you need to hit your second button on your calculator. So turn it on, hit your second button. And then all the way down to the bottom, right above the 0, it says catalog. So hit that and hit enter. All right, and hit, oops, what's happening here? It looks like the calculator is freaking out a little bit. So I'm going to do it again. Second catalog. There we go. All right, and then what I want you to do is just scroll down until you get to the D's. All right, and you should go faster than what I'm seeing on the screen here. This product here is really terrible. Used to be better, but whatever they're creating now for this is awful. All right, so get down to the D's, and what I want you to look for is a what's called diagnostic on. So I'll keep going, but you're probably ahead of me already. Diagnostic on. When you get the diagnostic on, I want you to hit the enter key. Almost there with me here. Again, you may already be there. There, that's diagnostic off. We don't want that one. We want diagnostic on. Hit enter. And then hit enter again. Now, what we have essentially done is we've added the correlation coefficient to your calculator. It'll show up somewhere, and I will show you where to find it. All right. So everybody should have done this. If you haven't, you'll need to go back and watch this video again, and it'll explain how to do it. You can also, of course, Google how to do this on your TI 8384 calculator, how to add the correlation coefficient onto your calculator. All right, but that did it right there. All right, so let's actually move away from here, and we'll use the calculator in a minute. Let's see what our time is. I think we have enough time to show you everything in these 2 sections. All right, stop sharing. Back to this. Let's see, so this is the definition, the measure of the strength and direction of the linear relationship between 2 numerical variables. There's your definition right there that I mentioned. It's always good to write things down also. And again, formula, the only reason you would ever use it is because your calculator is broken. Literally, you don't want to use it. It's a real pain. All right, so in this example here in the book, we're not going to get into all the details of it, but they have two variables that we are, and one of them is going to be an x variable, which again, the x variable is what? That is going to be your explanatory variable, and your y is going to be your response variable. Think of it that way, all right? One of these is going to be x, the other one's going to be y. And it'll be explained in the problem, whatever problem that you're looking at, which is which. In this case, the face width, the height ratio, whatever that is your explanatory variable, and the percent trusting is your y variable. And they created a scatter plot, all right? And then they ask you to what? Calculate the correlation coefficient, and it comes out to negative 0.39. The negative means if we drew a line through these points, it would be trending downward. But because these points are so scattered around that line, it's a pretty weak relationship. It's not a strong relationship. So the 0.39 is closer to 0 than it is to positive 1. Now, I should let me mention something to you about correlation coefficient. Once it's calculated, the lowest value it can have is -1, and the highest value that it can have is +1. -1 means perfect negative correlation. That means if we drew a line through the points, every point would fall on that line. That's what we saw in algebra, right? When we drew points on a line. +1 means all the points, if we drew a line that's sloping up towards the right, every point would be on that line. That's perfect positive correlation. Anything in between is the real life. 0, which is absolutely between -1 and 1, that means no correlation, no linear correlation. And then any numbers that are closer to 0 than they are to either +1 or -1 would be considered to be weaker correlation. Okay, and then they show you with all this formulas and stuff, how to calculate it. Again, I don't want you to look at any.
Could you repeat that?
Say again, what was that?
Could you repeat that? You said numbers that are closer to 0 are what in correlation?
Weaker.
Okay.
When we talk about strength, that's what we mean. Numbers that are closer to either +1 or -1 are stronger. Numbers that are closer to 0 are weaker. Okay, and then the rest of this section here is simply looking at the formulas, how to do it with formulas. We're not going to do that. And then properties, again, as I said, the properties, you may want to look at this because it says R, which is the symbol we use for the sample correlation coefficients between -1 and 1. And here, you know, what I just said about strength, you can look right here. All right, now, this is the author's opinion about what weak is. They say anything less than -0.5 is weak, or greater than 0.5 is moderately stronger. It's a matter of opinion on that, but certainly it's weaker when it's closer to 0, and stronger when it's closer to 1 or -1. Okay, so don't worry about that so much. That's not really that important in terms of what we're going to be doing, but certainly if you were comparing two correlation coefficients or looking at two scatter plots, and one looked like the points were closer to the line, that would obviously be a strong linear relationship. And if the points were not close to the line, that would be a weaker one. Okay, does that make sense? That's all you really need to know. So weaker means more scattered, strong means close to the line. All right, and then they define what perfect negative correlation is here when R is -1. Excuse me, perfect positive correlation when R is 1, and perfect negative correlation when R is -1. I explained that already. Another property is it's a measure of the extent to which X and Y are linearly related. R does not, and in number 4, R does not depend on the units of measurement for either variable. Units of measurement are canceled out in the calculation of correlation coefficient. That's something you would not know unless you were actually calculating it. And it says that the value of R does not depend on which of the two variables is considered X. In other words, If we switched x and y, if we called one variable, which was previously x, we called that y, and the other one, which we called y, we called that x, it wouldn't matter. The correlation coefficient would be exactly the same. Okay, and then they give you some more examples of that. All right, and finally, what I want to show you for the last 5 minutes is how to do all these calculations on your calculator. But I want to show you one more thing from the next section. And by the way, the next section, 5.2, is way too complicated for what we're going to be doing, but it has some of the things that we're going to be doing. So I don't want to spend too much time on it, but here are the definitions once again. And remember, explanatory variable is the variable that is causing an effect on another variable called the response variable. They're using different terms here, so pay attention to the definitions here. Explanatory variable, which we used before, can also be called a predictor variable, and it can also be called independent variable. The response variable, another name for that is the dependent variable. You don't need to memorize it, you just need to know where to find it in case it comes up in a test or a quiz or something like that. It's right here. So I think you all know the difference between an explanatory variable and a response variable, and these are just different other words that mean the same thing. All right, so we don't want to spend a whole lot of time on it. Now, what we're going to do in what's called regression. What is regression? Regression is an attempt to draw what's called a best fitting line through your scatter plot, all right, through the relationship between x and y. You want to draw a straight line through it, and there's multiple lines that you can draw through it, but we want to create what's called a linear regression line. Now, if you remember from high school math, the equation for a line, well, you used to know it as y is equal to mx plus b, but for some reason, TI 84 and 83 calculator use other formulas. They may use A and B instead of M and B, but regardless, whatever number is multiplying the x is called the slope. That other number that's added to those, that slope times the x, that's the y-intercept. That's the number that's the value that where the line intercepts the the y-axis, right? You probably learned this many times in high school over and over again, right? Because you took multiple algebra courses and they talked about this line. Well, we're going to use it. We are going to use it. But what's really great about this is that despite all the math that they talk about here and all the formulas, your calculator does the equation for you. Right? Your calculator will do the equation for you. Now here, they're saying, well, what if we have an equation y is equal to 10 plus 2x? Well, you learn in high school how to graph it, right? Well, don't worry about it. You don't even need to do any graphing in this course. The calculator does all the graphing for you. All right, so that's an upward sloping line, slope of 2, y-intercept of 10, and intercepts the y-axis of 10. That's what they're trying to show you. All right. Here's a negative sloping line. That means the slope's going to be negative. Notice the number that's multiplying the x is -5. That means the slope is going down 5 units. And then remember what slope means. If the slope is -5, it means that the curve, the line is going down, decreasing 5 units vertically for every 1 unit increasing to the right. All right, that's what slope means. All right, and then they use this term called principle of least squares. Again, this is a mathematical technique to come up with that line. And what they do is they take and I'll just tell you very briefly, but you don't have to know this very much. You look at the scatter plot. The line of best fit or the least squares line is what? It's the line where we look at the vertical difference between the actual point and the line itself, the vertical distance between those 2 points. And that's called the deviation from the line. And another name for that would be a residual, but we don't need to know that. And then what they do is they square those deviations from the line for each one of the points, and then they add them all up, and then they use calculus to calculate the to calculate the minimization of those sum of squared deviations. This may make no sense to you unless you've taken calculus, but what they're trying to do is find a line that is closest to those points that are scattered, all right? The line that's closest, and it's called the least square line. These are formulas that the people have come up with. We don't need to know those. All of this we used to have to do before calculators. And you're probably sighing a sense of relief here. And then finally, we have, I might run over it by about 2 or 3 minutes. I have an example of how to do this. And I'm going to share that example with the calculator. All right, I'll show you quickly how we do it. It's not that hard. And what I've done is, once I know my X variable and my Y variable, what I've done here, like if you go to stat, and what I've done is in L2, I put my X variable, all the numbers like we did before, but I did it in L2 because in L1 I have that's from the previous problem we were working on. So L2 is my X variable, all the numbers in the X variable, and all the numbers in the Y variable are in L3. You have to be very careful. You have to make sure that the X's and Y's match, all right? So you don't want to mix them up, all right? We don't want to sort them, do anything like that. We want to put them in the same order for both of these, same order, because remember, these are values that are for each observation. So height and weight, for example, it's for one person. So we don't want to mix up the, have somebody's height and somebody else's weight. We want to make sure it's the same height and weight. So these numbers are entered in the same order. Make sure of that, all right? Now, I typically put the X variable first, the Y variable second. So it's the X is in L2, Y is in L3. Now, if I want to find the line of best fit, what do? Very easy. I go to stat, hit the stat button. I scroll over to calc. We've done that before with one variable statistics. And now we're going to scroll down to number 4. All of you should have this, len reg AX plus B. Hit enter. And the only thing you have to do is for the X list, put where the X values are. In my case, it's in L2. Now, if it says L1 here, how do I make it L2? I hit second, 2. Same thing, if in my Y list, if my numbers are in L3, but it says L2 here, I'm gonna hit, I scroll down, and I'm gonna do second 3 for my L3. Then you have to scroll all the way down, hit calculate. And look what they give you the equation, y is equal to ax plus b. So a is the slope, b is the y-intercept. They give you those numbers. This is the slope, 3.136. The y-intercept's negative 357.78. And notice down here, at the bottom here, because we did that diagnostic on our calculator, it gives us the correlation coefficient. I want you to ignore the r squared. We don't use this in this course. Please ignore that. The correlation coefficient's down here, which means the line is going to be positive correlation. And notice the strength, it's moderately strong because it's bigger than 0.5. So it's positive. And by the way, the sign of the correlation coefficient will match the sign of the slope. So if the slope is positive, so will the correlation coefficient be positive. If it's negative, correlation coefficient will be negative. It sort of makes sense. So if I ask you for the equation, you simply plug in A into the equation and B into the equation. And of course, you include the X. So it would be Y is equal to, if we were rounding to 3 decimal points, it would be Y is equal to 3.136 times X plus negative 357.782 for the B. And that would be our line of best fit, what they call the line of best fit, or the regression line. And there's one other step that we would need to know. If I wanted to know a value of y for a value of x that's not in the data set, okay, I pick a value of x in the data set that's within the range of x's that we see in the data set, but it's not in the data set, and I want to predict what y would be using this line I simply take that value of x that's given and plug it in to the equation and then calculate y. This is something you did in high school in Algebra 2, and that is it. That's all you need to know for this. Now, one other thing I should mention to you is if the correlation coefficient is very small, close to 0, then the line of best fit it's not very good. It doesn't really work very well for approximating the linear fit, all right? So if the correlation is close to 0, the line of best fit is not really very good, all right? It has to be fairly strong, fairly moderate for the predictor of y based on some value of x, okay? I would recommend to read through these sections, but don't pay attention so much to the formulas. Try to get an idea of what I've talked about today. But as far as correlations are concerned and the line of best fit, that's how you do it. And finally, the last thing I want to show you, I know many of you may have to go, but I'm running a little bit over. I want to show you how to create a scatter plot. Now, to create the scatter plot, once again, you have to go to the window because you have to see it. And then what you want to do is you want to create a range for x's that would include all of the x's that are in your data set, all the x values. You want to create a minimum and a maximum so that all the values are in between that. I picked 100 for the minimum and 150 for the maximum because it happened to be in between. And notice the scale, I picked 10 because I wanted the notches to be every 10. I don't want it to be 1 because all the dots would be on top of each other if I did that. And then there was a negative value in the data set for the y's, so I made it -50, so I made sure that was in there, and I went up to 100 and to include all the numbers in the y's. Again, I made the y scale 10. So, and then what I did was, once I set up my window, I would go again to stat plot, second y is equal to my stat plot. I would hit enter. And the scatter plot is typically the very first one that you'll see. It looks like a scatter plot. So you want to scroll down and select that one. Make sure you hit enter because you might have used it for a histogram or a box plot before. And then once you have your scatter plot, you have to, once again, make sure your x's are in the right list. So if it says L1, you have to again do second 2. And the y's are in L3, so do second 3. And then once you have that completed, you hit graph, and there is the scatter plot. And it shows, it's always good to do a scatter plot, even if I don't ask you for it. Do the scatter plot so you have an idea of whether it looks linear or not. Okay, and this one sort of looks like it's going to increase. You picture a line of best fit going through there. And there's another little trick where you can also draw the line of best fit through this, but I'm not going to get through that now. All right, there's no need to do that. All right, any questions about how to create a scatter plot? Again, it's not something I would necessarily ask you to do, but it's something that you may want to do. All right, and that's it for this particular section. I'm just looking at a message here. If somebody wants to know when you say open book, open online textbook will be available. Yes, open book means online textbook. Oh, I see, for switching out. Well, yeah, I see what you're saying. So, oh, will it kick you out if you switch to the book? No, it shouldn't kick you out. You should be able to have multiple windows open where the textbook's open and Canvas is open also. So you can easily use the bottom bar of your windows to get to wherever you want to go. So you won't be kicked out. All right, that's it for today. It's a lot of material. Again, what I'm going to do is I'm going to post homework number 2 this week. It won't be as extensive as homework number 1. And it will have some review for everything I covered today. It'll be at least one question for each one of those topics. All right, and then on Wednesday, I will have a review for our first test. Wednesday will be a review for the first test, which will be next Monday. I'll go over what that is. I also have a vocab quiz on Wednesday, which will be just a review of the vocabulary that we went over today. All right, that's it, just vocab. And maybe, with vocab, maybe what we covered last time too. So I'll make it clear to you. But again, it'll be, if you've gone through the book, if you've gone through the videos, everything, it shouldn't be too bad. All right, any questions about that? No questions? All right, I'll stop the
Thank you.
recording. Yes, there was a question? I think you just said.
No, I was just saying thank you. Bye.
All right.